How do you achieve impedance matching 4 signal amplification stages? Imagine you're trying to pass a message through a series of pipes, but if the pipes don't fit together properly, the message gets lost or distorted. That's what impedance matching does in signal amplification. It makes sure signals flow smoothly from one stage to the next. When working with signals, each amplifier has an input impedance and an output impedance. To get the best signal transfer, these two need to match closely. If the output impedance of one stage is much lower than the input impedance of the next, most of the signal voltage makes it through without loss. This setup maximizes the voltage transfer and keeps the signal strong. One common way to achieve this is by connecting amplifiers in a cascade. For voltage amplifiers, the goal is to have the output impedance of the first amplifier much lower than the input impedance of the second. This creates an impedance bridge that allows maximum voltage to pass, boosting overall gain without losing signal strength. Sometimes, the impedances are not naturally compatible, especially when reactive components like inductors and capacitors are involved. In these cases, passive matching networks are used. These networks are made of resistors, inductors, and capacitors arranged in specific configurations, such as L networks, pi networks, or T networks. They help transform the impedance so that the real and imaginary parts align properly, which is essential for AC signals. In alternating current circuits, impedance includes reactance, which varies with frequency. To get maximum power transfer, the load impedance must be the complex conjugate of the source impedance. That means their resistive parts are equal, and their reactive parts are equal but opposite in sign. This cancels out reactive effects, allowing the maximum amount of power to flow from one stage to the next. Transformers are also useful tools. They can step up or step down voltage and current levels, effectively changing the impedance to match the next stage. High-frequency signals often travel through transmission lines, which have a characteristic impedance. Matching this impedance prevents reflections that cause signal loss or distortion. In real-world designs, perfect one-to-one impedance matching between every stage isn't always practical or necessary. Instead, engineers aim for an impedance ratio that maintains the desired gain and bandwidth. Sometimes, intermediate impedance stages are added to improve stability or reduce unwanted harmonics. When testing or measuring signals, equipment often assumes a standard impedance like 50 ohms. So, stages are designed to match this standard for consistency and compatibility. Proper impedance matching also helps prevent signal reflections that create standing waves, which can distort the signal and reduce the quality of the amplification. This is especially important in high-frequency or analog signal processing applications. To sum up, achieving impedance matching involves carefully designing or adjusting the input and output impedances of each amplification stage. This can be done with passive components, transformers, or transmission line techniques. The goal is to transfer maximum power, minimize signal loss, and keep the signal clean and strong throughout the entire system. This process is fundamental in analog signal processing and plays a vital role in everything from audio systems to radio frequency circuits.